Hello, ladies and gentlemen. My name is Mpeli Rampokanyo. I am the principal engineer at CSIR. I will be presenting to you an energy living lab, which is a mini grid that was designed at Upper Blinkwater in the province of the Eastern Cape. And then I will be focusing specifically on grid integration studies. Just to take you through the presentation outline, I will take you through the background to the presentation, study objectives, study assumptions. I will further discuss results and analysis, looking specifically at load flow studies and generator dispatch optimization results as well. I'll further look at dispatch strategy algorithm design and then conclude. So in terms of the background, as I have said, this is a microgrid pilot project that was initiated for electrification of the remote village of Upper Blinkwater in the province of the Eastern Cape in South Africa, which is situated 23 kilometers northwest of Fort Beaufort, which is an area that falls under the Raymond Mhlaba Local Municipality. The designed microgrid for the village is a hybrid system, which includes a photovoltaic system, a wind generator, a battery bank for storage, and a diesel generator for backup. We as the CSIR were appointed as partners in the project, specifically to spearhead the wind component of the project, and we are responsible as well for resource assessment, overall system integration, energy and grid modeling, and as well as knowledge transfer to the local university there, which is Fort Hare University. And still continuing, in terms of our capability as the CSR in the project, we are looking at a load assessment. As I've said, resource assessment was one of the areas we're looking at. System design, looking at the size and the configuration of the system. We did financial modeling, system optimization of generation dispatch. We looked at as well as project management of the entire project, including construction and monitoring and evaluation. Our stakeholders and partners included GIZ, German government was involved, and AfriCoast, and the Eastern Cape municipality, which is the Raymond Mhlaba Local Municipality, was also involved, and quite a lot of other stakeholders that I will not go through, but it was quite a number of them. In terms of the integration study scope and objectives, the project was, or rather the project objectives was to conduct a load flow study in order to assess the impact of integrating 6 by 3.5 kilowatt wind turbine generators to Upper Blinkwater microgrid, which was already made up of a 75 kilowatts peak photovoltaic system with a 2 by 65 kilowatt lithium ion battery bank and a 55 kVA backup diesel generator. The second objective was to conduct an optimization study that identifies the best possible dispatch strategy, which will minimize the occurrence of load shedding and excess energy on the microgrid. And the load flow study was done on Dix Island Power Factory platform, while the dispatch optimization was done on Homa Pro modeling environment. This just gives a schematic of the geographic layout of the area that we are talking about. It's made up of 65 households, a school and a church. And in terms of assumptions, the main key assumption was on load profile. As I've said, the village has not been electrified before and is not yet connected, obviously, to the local municipality there in terms of electricity. So then the problem was in terms of historical data unavailability, so that we could sort of like get a picture of the load profile. So then we went to the ESCOM and we requested the load profile for the larger municipality, which is the Bisho customer load network, which basically the Raymond Mhlaba Local Municipality falls under. So we got that load profile and scale it down to the Upper Blinkwater peak. So that's how we came up with the load profile of the area. So looking at the load flow scenarios that we studied, as you know, this type of studies, we are normally deterministic, and we look at extremities in terms of seeing how those particular extremities or conditions will stress the system. So if we look at, we looked at one scenario, which was a winter scenario, and obviously we are looking at a snapshot in time in load flow studies. So if you look at scenario 1, we looked at a time at 1300 where demand was 42.17 kilowatts with a generation of 34.7 kilowatts, which basically, as you can see, gives a deficit of about 7.4 kilowatts. So this deficit obviously can be, if the diesel generator is available, can be supplied by that diesel generator, or maybe the battery bank as well, if it's available in terms of charge. On the other scenario, at later in the day, around 1900, which is 7 o'clock in the evening, the demand was around 54.4 kilowatts, which coincides with a generation of 0 kilowatts. So basically, around that time, there is no renewable energy generation. And then obviously, this gives a deficit of 54.4 kilowatts. And as well, this deficit can be, if the diesel generator is available and the battery bank is fully charged, can be catered for by that. The other extreme scenario or condition that we looked at was a summer minimum loading, where obviously you would be expecting stresses in terms of voltages, voltage rise. But in this particular case, I am doing generator adequacy, and that's what I'm looking at. So when in terms of scenario 3 that we studied under this particular condition of summer minimum load, at around 11 o'clock, demand was around 35,000 kilowatts with a generation of about 56.6 kilowatts. That gave a surplus generation of 21.57 kilowatts. And this obviously can be used to charge the battery if the battery is depleted or has some space to take that charge. And then in the other scenario that we studied, looking at later in the evening, at around 2000, 8 o'clock in the evening, the demand of 44 kilowatts was supplied by no generation from renewables. So obviously that whole 44 kilowatts will be a deficit, which will need to be supplied by the battery bank or the diesel generator. So what do we take away from the load flow studies assessment that we did? Is that the load flow study by itself has limitations. Because why? Of this mismatch in load and generation. This particular condition calls for generator optimization studies that can be done obviously are time-based and can be done over the entire year to actually see the generation production together with the demand, whether the generation supply is available, it's enough to meet the demand in the area. So the constraint obviously is that the renewable energy generation is not dispatchable. And the main flexibility obviously can be offered by the battery and the diesel, which are obviously dispatchable type of generators that can supplement that renewable energy generation. So we're going to be looking at optimization studies for generator dispatch strategies that were done under the home environment. 4 strategies were looked at under the home environment, which is the cycle charge, the load following, combined dispatch, and predictive strategy. So the cycle charge, the generator operates at full capacity and excess power from the generator is used to charge the battery. Under load following, the generator in the system is used only to meet the power demands from the load, and the battery is charged by the renewables in the system. Under combined dispatch strategy, this one employs both the combined, or both the cycle charge and the load following. It uses cycle charge when net load is low and load following when net load is high. The net load is the difference between the load and the renewable generation. Under the predictive strategy, the algorithm is aware of future load demand, and it has a foresight of 48 hours, and it aims to maximize self-consumption of excess energy so that the energy curtailment can be minimized. So comparing this dispatch strategy that I've just talked about, if we look at the cycle chart dispatch strategy, it had an LCOE of R2.73. This obviously was with the generation mix of that 75 kilowatt peak of photovoltaic, 2 by 65 kilowatts battery storage, diesel generator, and 21 kilowatts wind turbine. So the levelized cost that I've set is R2.73 with an operating cost of 649,000 per annum. Load shedding occurred as well under this strategy to an amount of 10.2 kilowatt hours per annum, with an excess electricity production of 14,858 kilowatt hours per annum. And then if you compare this with combined dispatch strategy, this one had an LCO of R3.56, which is slightly higher than the previous case. And the operating cost here was 870,000 or so per annum. Further on, we further looked at predictive dispatch strategy. This one had an LCOE of R2.59, and obviously, as you can tell from that figure, it proved to be an optimal strategy for the region because of that lower LCOE. And if you look at the excess energy production, was around 6,362, which is quite low compared to the previous two cases. So the key takeaway here is that the predictive dispatch strategy is the optimal strategy to implement for this particular mini-grid. And although predictive dispatch strategy appears to perform better than the other dispatch strategy, there is still a lot of excess energy relatively produced that could be used for storage instead of dumping. So how do we do that? So then we have to optimize the battery size for optimal production of energy using a predictive dispatch strategy. And then we looked at different scenarios in terms of battery sizes. So we looked at the initial scenario constituted 2 batteries. And further on, we looked at different sizes of batteries, 4 batteries, 6 batteries, up to 8 batteries. Integrating this obviously with the predictive dispatch strategy. And from the results that we did, we found out that the 4 batteries with the predictive dispatch strategy, it will be an optimal size of the batteries that we would be required for this region when operating or using a predictive dispatch strategy for generation dispatching. So this particular 4 batteries gave an LCOE of R2.74 with an excess energy of 325 kilowatt hours per year, which is quite lower compared to the previous case of 2 batteries, which was 6,362 kilowatt hours of excess energy. So further on, we looked at the predictive dispatch strategy algorithm in terms of implementation, how it was supposed to be implemented on the ground. So we designed a logic diagram for this. And the logic diagram constituted a reserve margin of the algorithm that we came up with so that basically, as we remember, if we recap, the predictive dispatch strategy definition says the algorithm is aware of future load demand. It has a foresight of 48 hours, and it aims to maximize self-consumption of excess energy so that energy curtailment can be minimized. So we define a reserve margin for the forecast such that there is about a 30% reserve. So then under the predictive dispatch strategy, as I've said, we were designing the logic diagram that was going to be used for implementation on the mini-grid. And we had to define a reserve margin for this predictive dispatch strategy that basically puts a reserve of 30% for the forecast, so that we have a safe margin to make a decision whether to discharge the battery today in anticipation of excess energy tomorrow. But that excess energy tomorrow needs to have a margin of 30% when you compare it with the future consumption. So then we also had to go and input the cost of discharging the battery, which basically is just the cost of the battery wear, which is given by the formula that's reflected on the presentation. And then as well, we had to input the cost of turning on the diesel generator, which basically as well is given by that formula reflected there on the spreadsheet, sorry, on the presentation. So in terms of the predictive dispatch strategy algorithm, the algorithm obviously recalls the current load, the PV and the wind power, and it's sort of like compares that consumption, or rather demand, with the available generation, that is renewable energy generation. And if there is a deficit, if the battery state of charge is below or is greater than the minimum, then obviously we'll go into making a decision whether we want to dispatch the battery or the generator, depending on the cost of running any one of them. And then on the other hand, if you go to the left-hand side, then that's where now we have excess energy, where our demand is lower than our supply. Then obviously we'll have to make a decision in terms of whether that charge or that excess energy would be available to charge the battery. So that's the predictive dispatch strategy algorithm in a nutshell. So in terms of conclusions, the simulations have shown that the optimal dispatch strategy for wind case is the Homer predictive dispatch strategy, as it saves fuel over the entire life of the system and has a lower LCOE of 2.59. The combined dispatch strategy and the cycle charge dispatch strategy have shown not to be optimal when compared with the predictive dispatch strategy. And also the optimal battery bank capacity was found to be 4 by 65 kilowatt hours, which will bring the total storage capacity to about 260 kilowatt hours. Obviously, this helps to reduce the excess energy from 6,362 kilowatt hours per annum to 325 kilowatt hours per annum. But also it has obviously the disadvantage that there is a additional capital cost of 920,000 onto the system for the additional 2 batteries. Further on, we anticipate that obviously there will be increasing future demand in the grid. It is expected that the demand in the mini grid may increase in the subsequent years, as obviously current households increase their consumption and as more households are being electrified. This future increase in the load will work out positively, as it will help to reduce the amount of excess energy seen currently. However, the likelihood of load shedding may also increase as the demand increase. This is all, of course, because of the variable nature of renewable energy, as it is mostly plentiful when not in demand, that is at daytime, and scarce when really demanded, that is obviously in the evening. Thanks a lot. I can take questions now, and if I cannot address them at this point in time, then we'll address them later. Thanks a lot.